Now, I did a quick review of what I expected people knew from first year calculus, but I know darn well that first year calculus courses sometimes do a little multiple integration, but often they don't, especially if they do as ours does, and that's where everybody had it. A really good job on sequential series, Taylor series, and so forth. Okay, so I wrote all this down and then realized that people didn't already know it, so I wasn't reviewing, and this isn't enough to introduce the topic, so we went over to here and worked it out in a little more detail. Okay, so what we have is a circle of radius A. We want to find the area of the circle. Okay, now there are simple ways. You can slice the circle up into little pie-shaped regions, and just imagine the pie shape. You have more and more pie-shaped regions. You can stack them into something that's almost a rectangle, whose dimensions are 1/2 of the circumference times the radius, which is then pi r squared. But we're going to do it using integration. Okay? Well, we start by partitioning the interval from x equals -a to a. And our partition is just going to be this. Okay, so let's just remind ourselves that we have -a here on the axis and a here on the axis. There's an x interval from -a to a. We break it up into subintervals. I've indicated that here, but of course we think in terms of breaking it up into a very large number of subintervals, so the intervals are very, very short. Well, each interval of that partition corresponds to a part of the circle. We just take vertical lines through these points on the x-axis, and we have the part of the circle that we're going to associate with that interval of the partition. Now, in each interval of the partition, we have a sample point that I'm going to designate by x sub I star, and that will be the sample point in the ith interval. So let's assume that what I've got here represents the ith interval, the part of the circle that corresponds to the ith interval, the vertical strip corresponding to that part, to that subinterval, and a sample point x sub I star. Now there's an arrow here, but this is the coordinate, and this orange line then goes through that coordinate. Okay. Now, the width of this region is delta x sub I, and we're going to say that the y values go from here to here, from this point on the circle to this point. Now these points correspond to x coordinate x sub I star, so by the Pythagorean theorem, right triangle from here to here to here and back has hypotenuse A. This leg is x sub I star, so that this looking for a word. This distance here, this displacement here, whatever this is just the square root of a squared minus x sub I star squared. And same with this one. We do the same type of triangle, and this distance will be the same. So the y value down here, of course, will be negative square root of a squared minus x sub I star squared. The y-coordinate up here will be positive square root of a squared minus x sub I squared. Again, just a very straightforward application of the Pythagorean theorem. So that this dimension, or let's just say that y values are going to go from this to this. Okay? And we're going to ignore any part of this rectangle, or we're going to make a rectangle out of this. And we're going to say, okay, the area of this portion of the circle is very close to the area of this rectangle, to the extent that our interval is small. our subinterval is small. So if all our subintervals are very small, there's very little difference between the area of the rectangle and the actual area between the two vertical lines within the circle. Okay, so we're going to say the area of the ith interval is therefore approximately equal to this dimension, which is going to be 2 times the a squared minus xi star squared. We have one here and we have one here, and besides, if we subtract this from this, this is what we get. And we multiply that by the width, which is delta x sub I, so that the sum of all the areas that we get for all of our intervals of the partition will be the sum from I equals 1 to n of this expression. And that, by the process that you should be used to, approaches the integral. Integral from what to what? Well, we partitioned the interval from negative a to a, so your x values go from negative a to a. And for each x value, we have an area here, which would be represented by 2a squared minus x squared, not times the delta x anymore, but times dx. I'm waving my hands a little bit here. We can do this rigorously, but we don't want to push it too hard. Okay. So there's our integral, and you can do that integral, simple trig substitution, and we get pi a squared. And when I say it's a simple trig substitution, it's one that you haven't thought about. You're going to let x equal a cosine theta, for example. But if you haven't thought about it for a while, it's not trivial. You want to remind yourself, because you're going to have to do a lot of those. Okay. Anyhow, there it is. And that is the right formula. Now, we didn't do any multiple integration at all. Okay? But to motivate multiple integration, we're going to assume that there's some mass density given by the function rho of xy. So if we multiply the average mass for a region, the average mass calculated from this function, by the area of the region, we get the mass of the region. Okay. So we're going to see how a further partitioning, a partition of, well, we partition along the x-axis and we get these strips, and then we partition each strip with respect to y, and we get little rectangles, so that a continuous density function on any rectangle won't differ by a whole lot from one point of the small rectangle to another. And we then get an integral, and it's going to end up being a double integral, and we'll work through that in the next clip.